Hello everyone, welcome to the e-learning series. Now today I am going to take the second lecture on the fifth chapter. The topic of the today's lecture is the remaining characteristics of laser, coherence and the problem based on the coherence. Friends, in the previous lecture I have taken the three characteristics of the laser such as the directionality, monochromatic and the intensity. Friends, today we are going to see in details about the fourth characteristics of the laser, coherence and its types. Basically, there are the two types of the coherence. One is temporal coherence and second one is the spatial coherence. And the problem based on the coherence. Friends, we are going to see in details about what do you mean by the coherence. In the first chapter, I have already told you about the different characteristics of the laser. Coherence is one of the characteristics. The any light from or the light from a source is said to be coherent, which means that the wavelength of the laser light are in a phase, in a space and the time. Due to that, the light from the laser is said to be coherent. Now basically, in case of that, the coherent light in which the all components propagating through the medium, they should be in a phase or they should travel with an equal phase. We know that an ordinary source of the light, such as the light emitted from the electric bulb, emit in all directions randomly. And the light waves emitted by and the ordinary source of the light spread in all directions and are not in a phase with each other. Now here in this figure we can see, now these are the number of the waves they are propagating in a space. Then we can see that the phase of all these waves are not in the same phase, and due to that they are known as the incoherent waves. Such a beam of the light whose component waves are not in a phase with each other is called the incoherent beam of the light. If the incoherent waves combine, then the amplitude of the resultant wave is always less than the amplitude of any of the combining waves. That means if we add all these waves, then the amplitude of the resultant wave will be decreases because all these waves are not in a phase. So the students, remember about what do you mean by the incoherent. However, the light waves emitted by the laser are always in a phase with each other at every point in the space, and due to that the laser light beam is known as a coherent beam of the light. Now see here, in this figure we can see that now here the number of the waves are propagating in a space. These waves are emitted from a source of the laser. Then we can see that the every wave are in a phase with each other. And if we combine all these waves, then the amplitude of the resultant wave will be always greater than the amplitude of any of the combining waves. That means if we add all these waves, then the amplitude of the resultant wave will be increases. The coherence is a measure of the correlation between the phase measured at the different points on a wave. And according to that, there are basically the two types of the coherence. The one is temporal coherence. Now it is also known as the longitudinal coherence. And this coherence is related with at the time. And second one is the spatial coherence. It is also known as the transverse coherence. And this type of the coherence is related with the space. So the students, you have to be remember that the coherence is a measure of the correlation between the phases measured at the different points in a wave. And that means here the coherence is related with the time and the space, and according to that, basically there are the two types of the coherence, that is the temporal coherence, and second one is the spatial coherence. So we are going to see in details about what do you mean by the temporal coherence and what do you mean by the spatial coherence. Now then, first one is the temporal coherence. The temporal coherence is concerned with the phase correlation of the waves at a given point in a space at the two different instants of the time. That means here the temporal coherence is gives the relation with the phase correlation of the waves at a given point in a space at the two different instants of the time. That means when the waves get propagating along the same direction, now that times the temporal coherence gives the phase correlation of the waves at a given point in a space at the two different instants of the time. The temporal coherence is also a measure of the correlation of the light waves phase at the different points along the direction of the propagation. In shortly, we can say that the temporal coherence tell us how the monochromatic a source is. That means when the waves are propagating, and that times these waves should be the monochromatic. The type of the coherence related with the time, and it is also known as the longitudinal coherence. So the student, you have to be remember that the temporal coherence is related with that the time. The temporal coherence of the light is related to the frequency bandwidth of the source. If it is related with that the time, then we can say that it is also related with the frequency bandwidth of the source. Now see here, from these two figures we can easily understand about what do we mean by the temporal coherence. Now let us consider a single wave propagating along the x direction. Now let the electric field vector at the one point in a space at the two different points, at the two different times, say as the t1 and the t2. Now here we can see here a single wave is propagating along the x direction. Suppose if we consider here the propagating wave is an electric wave vector, then at one point in a space at the two different times, say as the t1 and the t2. Let the phase difference between the field wave vector E1 at the t1 and is phi1 and E2 at t2, say as, the phase difference between the field E1 at the T1 and E2 at the T2 be phi 1. Now see here in the first figure A, we can see that the phase difference between these two points, that means at the two times, the T1 corresponding times T1 and T2, we can see here, or we can say that the phase difference at these two time is the phi 1. Now let the electric field vector after that the time T3 and the T4. Now then let here, if we consider the phase difference between the field vector E1 at the T3 and at the T4 is phi 2. Then if the phi 1 becomes equal to the phi 2, then and is true for the any time interval of the same duration, then we can say that the wave is said to be the temporal coherence. That means here we can say that when the wave is propagating along the same direction, now then at the any instant during the propagation, the phase difference should be same, and such a type of the coherence is known as the temporal coherence. The temporal coherence may be expected only for a short distance in a space and for a time. Now, in view of this, temporal coherence is characterized by the two, namely coherence parameters such as the coherence length and the coherence time. Now here, the coherence length and the coherence time measure how long the light waves remains in a phase when they travel in a space. Now see here, from this figure we can see here. Now when the waves is propagating and after that the collision, we know that the phase of the wave will be get changes. Therefore, the distance and the time along which the phase of the wave will be get maintained will be the remains constant. Now then, such a length is known as the coherence length, and the time required during which the wave will remains in a phase, then that time is known as the coherence time. The coherence length depends on the central wavelength, the lambda, and the bandwidth, say as the del lambda of the wave packet. Now see here in this figure we can see here. Now this is the intensity graph plotted with the change in the wavelength, and we can, now we have already seen about such a type of that the graph. Now here this is the wave function. Now then, the coherence time is given as, we know, is given as here, that is the coherence time, it is equal to be the L divided by, that is coherence length divided by the C, where C is the velocity. Therefore we can write the coherence time in terms of the frequency. The coherence time, it is the reciprocal of the frequency, so we can write the 1 divided by the nu, it is equal to be the L coherence divided by the C. So we get the nu, it is equal to be the C divided by the L coherence, and therefore we can write here in terms of the bandwidth, that is the del nu, it is equal to with c divided by the coherence length here. We know that the relation c, it is equal to the nu lambda. Therefore, the nu, it is equal to be, by rearranging the terms, the nu, it is equal to the c divided by the lambda. By taking the differentiation, now we can write the del nu, it is equal to be the minus c into the del lambda divided by the lambda square. Now by substituting the value of the del nu in the above equation of the del nu, we get the c divided by the L coherence, it is equal to the c into the del lambda divided by the lambda square. Therefore, we can write here the by cancelling the c on both sides, we get the coherence length, it is equal to be the lambda square divided by the del lambda. Therefore, the coherence length, it is equal to be the lambda square divided by the 2 lambda. So the friends, you have to be remember that how we can obtain the expression for the coherence length. Now see here, the average time interval for which the definite phase relationship exists is known as the coherence time, and the distance L for which the wave field remains sinusoidal is known as the coherence length. The coherence length is also a very small measure of the temporal coherence because it tells us how far apart the 2 points along the light beam can be remains coherent. So here, before the collision and after the collision, we can see that in between these 2 points that the beam will be remains coherent with each other. That is, the temporal coherence measure the continuity of the wave along its length. The temporal coherence is the characteristics of the single beam of the light, and the temporal coherence tell us how the monochromatic is the source. That means during the interval between the two collisions, it will be the remain. Now we are going to see the second type of the coherence, which is known as the spatial coherence. The spatial coherence is concerned with the phase correlation of the two different points across a wavefront at a given instant of the time. Now that means when the two waves are propagating in a space, then the spatial coherence gives the correlation of the two different points across the wavefront at a given instant of the time. Now that means, now see here, these are the two waves are propagating in a space. Now then here we are considering the 2 points, say as the P1 and the P2. So here the spatial coherence gives the correlation of the phase of these two waves at the two different points. In another way, we can say that the spatial coherence is a measure of the correlation between the phases of the light wave at the different points transverse to the direction of the propagation. The spatial coherence is also known as the transverse coherence. Friends, you know that the transverse propagation in which the particle of the medium is perpendicular to the direction of the propagation. The spatial coherence tells us how uniform the phase of the wavefront is. That means during the propagation, in a spatial coherence, how it will maintain the phase correlation between the 2 points. Now to understand the concept of spatial coherence, now let us consider the two identical waves traveling along the same directions but are at a distance from each other. Now let us compare here their phases at the same time. Now say as the time t1. Now see here the electric field vector say as the point p1 is e1 and the electric wave vector at the point p2 is say as the e2. Therefore from this figure we can say that the phase difference between these two electric wave vectors is 0 because at these 2 points the p1 and p2 the phases of these two waves are the same. Therefore we can say that the phase difference between these two waves at these two different points is the same here. Now let us consider the same two waves at some later time say as the t2. Now which is shown in this figure B. Now here the electric field vector E1 is at the point P1 and E2 as the point P2 are different than that they were at the T1. Now that means here the points P1 and P2 after the some instant say as the time T2 its position is at the different points. If the phase difference between the two electric wave vectors remains 0 for all times, then the two waves are said to be a spatial coherence. So in this figure we can say that after the time t2, these two wave vectors will maintain the same phase at the point p1 and at the point p2. Therefore, after the time t2, the phase difference between these two waves is again the same. Therefore, we can say that if the phase difference between these two electric wave vector remains same for all times, then these waves are said to be a spatial coherence. So remember that what do you mean by the spatial coherence. Now consider here the width is at a distance along the wavefront within which the amplitude and the phase of the wave can be considered. And the phase of the wave can be considered well defined and therefore predictable. The spatial coherence is determined by the coherence width say as the WC. Therefore, from the geometry of this figure, the coherence width is expressed as the WC, it is equal to the K into lambda divided by the D into R. Now here K is the constant depending upon the shape of the source. D is the approximation diameter of the source. Now see here this is the D is the diameter of the source. R is the distance from the source. Now see here these 2 points they are at a distance R from the source. Therefore we can say that the spatial coherence is related with the position and the spatial coherence is related to the size of the light source also. Now see here. Now this is the diagram of the Young's experiment. Now see here, this is the ordinary source of the light say as the bulb which emits the radiation in a different directions. Now if we pass this radiation through a pinhole of the aperture. Now then we can see here the wave propagating after the pinhole aperture. Then these propagation of the waves are the type of the spatially coherent. If these waves are passing through a wave filter, now then we can observe that all these waves are in the same phase, and due to that they are known as, or these waves are known as the coherent type of the waves. So here in this figure we can understand that when the number of the waves which are emitted from the any source, and when they will passing through a pinhole aperture, now then it produces a special type of the coherent radiations. Now then here we can distinguish about the temporal coherence and the spatial coherence. Now we have seen that the temporal coherence is concerned with the phase correlation of the waves at a given point in a space at the two different instants of the time. Means if we measure the phase correlation between the two waves at the two different points, then it will be the remain same. But now in case of the spatial coherence, the spatial coherence is concerned with the phase correlation of the two different points across the wavefront at a given instant of the time. Now that means here at the two different positions, after the some interval of that the time, the wave should be remains in the same phase. The second point is the temporal coherence is related with the time, while the spatial coherence is related with the position. The temporal coherence is also known as the longitudinal coherence, while the spatial coherence is known as the transverse coherence. The temporal coherence of the light is related to the frequency bandwidth of the source, and it maintains the monochromaticity, while the spatial coherence is related to the size of the light source. The temporal coherence tells us how the monochromatic a source, while the spatial coherence tells us how uniform the phase of the wavefront is. The temporal coherence measure in interferometer such as Michelson's interferometer, while the spatial coherence measure in interferometers such as the Young's double slit interferometer. So remember the difference. Remember the difference between the temporal. What is the difference between the temporal coherence and the spatial coherence, and how we distinguish it? Now then we are going to take some problems based on the coherence. The first example is the fluorescent tube light emits the visible light of the wavelength in the range of 4000 angstrom and the 7000 angstrom with average length the 5000 angstrom. Then calculate the coherence length and the coherence time. Now student, first you have to be write the given things here. So the lambda is given, that is the wavelength is given, and it is equal to be the 5000 angstrom unit, and you have to be calculate here the del lambda, and it is difference between the two wavelength. Therefore the del lambda, it is equal to be the 7000 minus 4000, and it is equal to be the 3000 angstrom unit. So you have to be calculate the coherence length and the coherence time. By using the formula of the coherence length, it is equal to the lambda square divided by the twice del lambda. By substituting the values, we get the coherence length, it is equal to the 4167 angstrom, and by using the formula of the coherence time, the T coherence, it is equal to be the L coherence divided by the C, where C is the velocity of the light. Then by substituting the value of the coherence length and the velocity of the light, we get the coherence time, it is equal to be the 1389 into 10 raised to minus 18 second. Now in this way, if you know the formulas of the coherence length and the coherence time, now then by substituting the values, we can determine the coherence length and the coherence time. The second problem is the light from the helium neon laser, which is the traditional monochromatic source, has a coherence length of 100 meter and the wavelength 6328 angstrom. Then calculate the bandwidth of helium neon laser. Now you have to be write the given things. The wavelength lambda is given and the coherence length is given. So you have to be calculate the bandwidth, that is the del lambda. Now by using the formula of the coherence length, it is equal to be the lambda square divided by the 2 del lambda. Now by rearranging the term, now express it in terms of the del lambda, and it is equal to be the lambda square divided by the 2 twice into coherence length. Now then by substituting the values, we get the bandwidth, it is equal to be the twice into 10 raised to minus 5 angstrom unit. So now in this way, we can calculate the problems related with the coherence length and the coherence time. Friends, in this chapter we have seen the one of the characteristics of the laser, that is the coherence and its type, the temporal coherence and the spatial coherence, and the difference between the spatial coherence and the temporal coherence and the spatial coherence. So, and we have solved the two problems also based on the coherence length and the coherence time. So, friends, you have to remember all the four characteristics of the laser and the types of the characteristics. That means what do you mean by the coherence? What are the different types of the coherent sources? And in this way, the chapter is over.